Section: Introduction. In this section, we delve into the exploration of deep learning, which has traditionally been centered around digital media files like text, audio, and images. These formats are straightforward for humans to understand and are crucial for our communication. Text, for instance, is a key medium for sharing human knowledge and has led to the development of language models, LMs. The core idea behind LMs is to break down text into smaller pieces, known as tokens, and then predict what comes next in the sequence. This process helps these models grasp human language and intelligence. Recently, this concept of tokenization has expanded to include different types of data, allowing LMs to gain a more comprehensive understanding of the world and better mimic human intelligence. However, these models mainly focus on media data and often overlook the vast amount of native binary data that exists in the digital realm. Since bytes form the basis of all digital content, devices, and software, we believe that training models to predict the next byte could revolutionize deep learning, enabling models to fully understand and replicate digital world activities. This could have significant implications not just in traditional areas but also in less explored fields like cybersecurity, computer diagnostics, data compression, and reverse engineering software from its binary form. In this paper, we introduce bGPT, a model we've designed specifically for processing binary data and modeling the digital world through next byte prediction. Unlike traditional deep learning models that focus on digital media, bGPT encompasses the broader digital ecosystem, including hardware architectures and complex algorithms. By directly working with binary data, bGPT offers a deeper and more integrated understanding of the digital world. Its benefits are twofold. Firstly, it can interpret digital systems by learning from byte sequences, which enables it to predict, simulate, and diagnose behaviors in algorithms or hardware. This capability could even allow for the reconstruction of complex systems from their binary data. Secondly, bGPT unifies various data types under a single framework by treating everything as a sequence of bytes, simplifying modeling and facilitating the integration of diverse data sources. Our experiments cover two main areas: traditional tasks like generative modeling and classification on digital media data, e.g., text, audio, and images, and more novel tasks that are intrinsic to binary native operations, such as data conversion and CPU state modeling. These latter tasks are crucial for simulating algorithms and hardware. Our exploration into byte models represents a significant step towards a more holistic and unified approach to deep learning, offering a fresh perspective on modeling the digital world. Background on language models, LMs, reveals that from earlier LSTM-based models to the more recent transformer-based ones, LMs have been instrumental in understanding and generating human language, thereby simulating human intelligence. The process of breaking down text into smaller units, like words or subwords, is fundamental to these models. The advent of generative pre-trained transformer, GPT, models marked a significant advancement in this field. GPT models learn through self-supervised training, especially by predicting the next token in a sequence from a large text dataset. This method enables them to understand the structure and meaning behind languages. The concept of next token prediction has been extended to various data types, enhancing models' capabilities in audio processing, music generation, image processing, and even in understanding biochemical sequences. Regarding byte models, although binary data doesn't inherently possess the structure and semantics of data types like text, recent research has begun to unlock its potential for modeling and information extraction. Models like MalCon-V and DeepVSA have shown promise in malware detection and program analysis by working directly with raw byte sequences. Furthermore, the idea of compressing byte sequences with language models opens up new possibilities for utilizing large pre-trained models. Research has shown the effectiveness of byte-level encoding for language tasks, improving multilingual model training and machine translation. Models like Byte5 and Byteformer have demonstrated the advantages of working with byte sequences, including better handling of noise and spelling variations in multilingual contexts. Despite these advancements, the focus has often been narrow, overlooking the broader potential of byte models in simulating the digital world. To bridge this gap, we've used bGPT to model native binary data and conducted extensive evaluations across a variety of tasks, providing a comprehensive view of the potential of byte models in different applications. Section Summary. In this section, we delve into the significance of language models, LMs, in deep learning, particularly their evolution from text tokenization to next token prediction for understanding human language and intelligence. We introduce bGPT, a model designed to process binary data by predicting the next byte, enabling a deeper understanding and simulation of digital systems beyond traditional media files. By training on byte sequences, bGPT can interpret digital systems, simulate hardware behavior, and unify various data types into a single framework, showcasing the potential of byte models in advancing digital world modeling and simulation. Section: Methodology. In this section, we introduce bGPT, a model we've designed to work with digital data right down to the byte level. We kick things off by explaining its hierarchical transformer structure, which cleverly breaks down byte sequences into smaller chunks, or patches, to keep things computationally manageable. Next, we dive into the training goals for bGPT, which include both generative modeling and classification tasks. When it comes to model architecture, dealing with data at the byte level is quite advantageous. It not only helps our model get a grip on the patterns found in digital systems but also allows us to handle different types of data within a single framework. However, the detailed nature of bytes means we're looking at very long sequences, which can significantly bump up the computational demands. This challenge is particularly acute with transformer-based models, where the need for self-attention calculations grows quadratically with sequence length, making it tough to efficiently process binary data. To tackle the issue of handling lengthy byte sequences in transformer-based models, we drew inspiration from previous studies and developed bGPT with a hierarchical transformer architecture. This approach involves breaking down a byte sequence, which we'll call B and consists of bytes from B1 to BT, into a series of patches, P, where each patch contains exactly S bytes. The total number of patches, N, is determined by dividing the total length T by the patch size S and rounding up if necessary. If the total byte length T doesn't divide evenly by S, we pad the final patch with an end-of-patch token to make up the size. By segmenting byte sequences into more manageable patches, bGPT strikes a balance between the need for detailed byte-level modeling and computational efficiency. As shown in our diagrams, bGPT is made up of three main parts: a linear projection layer, a patch-level decoder, and a byte-level decoder. Here's how it works. The linear projection layer takes each patch, views it as a matrix where each byte is represented as a one-hot encoded vector, including an end-of-patch token, flattens this matrix into a one-dimensional vector, and then transforms it into a dense vector of a certain size, H, through a weight matrix. This process effectively reduces the dimensionality of our data while keeping the essential information intact. The patch-level decoder then processes these dense vectors, predicting the features of the next patch in the sequence by learning the structure of the data. The byte-level decoder focuses on each patch individually, using the predicted features to reconstruct the sequence of bytes within that patch. For training bGPT, we primarily focus on generative modeling, where the model learns to predict the next byte in a sequence based on the bytes that came before it. This involves minimizing the negative log likelihood of these predictions across the entire sequence. After initially training on this generative task, we further adapt bGPT for classification tasks. Here, the model learns to categorize byte sequences based on labeled data, aiming to minimize the classification loss by accurately predicting the category of each sequence. Section Summary. In this section, we introduce bGPT, a model optimized for modeling digital data at the byte level using a hierarchical transformer framework that segments byte sequences into patches for computational efficiency. The model architecture of bGPT consists of a linear projection layer, a patch-level decoder, and a byte-level decoder, enabling efficient processing of byte sequences by predicting features of subsequent patches and reconstructing byte sequences within each patch. The training objectives of bGPT focus on generative modeling through next byte prediction to understand sequential dependencies in data and further adaptation to classification tasks by predicting categories from byte sequences. Section: Applications. In this section, we explore how byte models like bGPT are particularly skilled at understanding binary data, which includes processing digital media files such as text, audio, and images, as well as simulating algorithms and hardware operations. These capabilities allow for a deeper analysis of software and digital systems. We introduce the applications we've selected and the experimental setups we've used to evaluate bGPT's performance. Starting with digital media processing, we've seen that the field of deep learning is making significant strides in generating and classifying various types of media, which are crucial for human communication. These media files are often stored and transmitted as byte sequences on electronic devices, making them accessible for bGPT to process. bGPT is trained to model generatively, learning to predict the next token in a sequence, and then uses the features from the final layer of its decoder for classification. To make training more efficient, we standardized the formats of audio and image datasets. For audio, we converted files to WAV format, ensuring they had a sampling rate of 8000 Hz, were mono, and had an 8-bit depth, with each file trimmed to 1 second. For images, we used BMP format with a resolution of 32 by 32 pixels, in RGB color, and with a 24-bit depth. When it comes to simulating algorithms and hardware, we chose 2 examples to showcase the abilities of byte models, data conversion and CPU state modeling. For data conversion, we focused on converting between symbolic music formats, specifically ABC notation and MIDI files. bGPT was tasked with learning to convert from text-based ABC notation to binary MIDI signals and vice versa, which requires understanding and reverse engineering the conversion algorithm. For CPU state modeling, we fed bGPT sequences of machine instructions followed by CPU register states, aiming to predict how the state changes with each instruction. We introduced a dataset for this purpose, containing instances that simulate typical CPU behavior, despite being simplified for easier data collection and evaluation. In our experiments, we used open-source datasets across various domains, including images, speech, text, symbolic music, and CPU states. The training settings for all bGPT models were consistent, supporting file sizes up to 8 kilobytes with a patch size of 16 and a sequence length of 512. Our bGPT model, with 110 million parameters, aligns with the scale of standard transformer-based models. We avoided hyperparameter tuning and data augmentation to ensure a fair evaluation, using accuracy for classification performance and bits per byte for generative modeling tasks. Specifically, for digital media processing, we aim to assess how well bGPT can process digital media files at the byte level compared to specialized models. We followed the standard approach of pre-training followed by fine-tuning. bGPT was pre-trained on diverse datasets, including ImageNet, Wikipedia, and LibreSpeech. We also tested the impact of mixed pre-training, combining datasets in different ways, and compared these to a randomly initialized model. These models were first fine-tuned using next byte prediction on specific datasets and then further fine-tuned for classification tasks. Section Summary. In this section, we introduce applications of bGPT in digital media processing and algorithm, hardware simulation. We demonstrate bGPT's ability to process diverse media types like text, audio, and images, and simulate digital processes such as data conversion and CPU state modeling. Our experiments show that bGPT excels in generative modeling and classification tasks, showcasing its proficiency in understanding and analyzing digital content at the byte level. Section: Baselines. In this section, we discuss the benchmarks we used for comparison and the results we obtained. We chose transformer-based models of a similar size that are known for their excellence in specific domains for our baseline comparisons. These include GPT-2 Small for text generation and classification tasks, and VIT B16 and AST for image and audio classification tasks, respectively. The GPT-2 Small model was initially trained on the English Wikipedia, using the same settings as our bGPT model. Both VIT and AST models were pre-trained on the ImageNet dataset, and we referred to the original studies for their results. For the CIFAR10 and Speech Commands V2 datasets, where there were no benchmarks for generative modeling, we did not include BPB, bits per byte, metrics in our report. The results, as shown in Table 3, highlight the significant impact of pre-training on the performance of models across all tasks. For instance, our bGPT model that was pre-trained on Wikipedia data showed strong performance in tasks related to text, while the variant of our bGPT model pre-trained on Libri speech data outperformed others in tasks involving spoken content. This demonstrates that our bGPT models can achieve better results in specific tasks when the data used for pre-training closely matches the data used for fine-tuning, which is in line with the principles of pre-training. Despite not being specifically designed for certain modalities, our bGPT models still manage to perform comparably to the baseline models. For example, our bGPT model pre-trained on Wikipedia data achieved a BPB score of 1.0639 and an accuracy of 92.49% on the AG News dataset. Although this did not quite reach the performance of GPT-2 Small, which scored 0.9237 BPB and 94.50% accuracy, it still shows competitive performance. Similarly, our bGPT model pre-trained on Libri speech data achieved an accuracy of 96.03% on the Speech Commands V2 dataset, which is close to the 98.11% accuracy of the AST model. However, we observed a noticeable difference in performance on the CIFAR10 image classification task, where our bGPT model pre-trained on image data lagged behind the VIT model, achieving an accuracy of 88.69% compared to VIT's 98.13%. This gap in performance for image tasks is likely due to the sequential processing nature of Byte models, which may struggle to capture the essential two-dimensional spatial relationships in images. Interestingly, our bGPT models pre-trained on mixed modalities, such as those involving both signals and a mix of data types, generally performed in line with the average performance of models pre-trained on single modalities. For example, our mixed modality bGPT model on the AG News dataset outperformed other variants with a BPB of 1.0935 and an accuracy of 91.75%. Yet it did not surpass the performance of our text-specific bGPT model. This suggests a trade-off in Byte models. While mixed modality pre-training offers versatility, it may compromise the depth of understanding in specific domains. We also observed mixed results in cross-modal fine-tuning of our bGPT models, with both positive and negative transfer effects. Positive transfer was seen when models pre-trained on one type of data, such as audio or images, were fine-tuned on tasks of another modality, showing improvements over starting from scratch. This indicates that there are shared byte patterns between different modalities like audio and images. However, negative transfer was noted when moving between text and other modalities, suggesting that the structured pattern learning beneficial in pre-training does not universally apply across all types of data. Text, being a human-created abstraction, has unique byte-level organizational patterns that differ significantly from those in audio and visual data, which may explain the observed negative transfer effects in text-related cross-modal fine-tuning. To delve deeper into the dynamics of cross-modal knowledge transfer in Byte models, we evaluated their performance on the Speech Commands V2 dataset, transformed into 32 by 32 BMP spectrograms. This conversion from 8 kilobytes audio files to 3 kilobytes images inevitably results in information loss. However, our focus was on exploring the nuances of knowledge transfer rather than just performance metrics. We selected two pre-trained models for evaluation. One pre-trained on image data for its format consistency with spectrograms and another pre-trained on Libre speech data for its content similarity with spectrograms. These models were used for both conditional generative modeling and classification, following a similar procedure to that described in Table 3. The results showed closely matched BPB between the two models, suggesting that the performance disparity observed in their CIFAR10 results does not extend to this spectrogram-based task. Notably, our model pre-trained on audio data achieved higher accuracy on spectrograms with speech content than the one pre-trained on image data, indicating effective cross-modal transfer and the importance of content alignment over data format. This demonstrates that Byte models have an inherent ability to recognize and translate abstract data features and patterns, regardless of the specific format or modality of the input. Together, these findings confirm the versatility and adaptability of our bGPT models in processing digital media data and transferring knowledge across different modalities, even when the formats of the data differ. This highlights the potential of Byte models to integrate shared knowledge from various sources, enhancing our understanding of the digital world. Section Summary. In this section, we compared bGPT models with transformer-based baselines like GPT-2 Small, VIT, and AST across various tasks. We found that pre-training significantly impacts model performance, with bGPT models excelling in tasks aligned with their pre-training datasets. Despite lacking modality-specific knowledge, bGPT models still perform competitively with baselines, showcasing potential for state-of-the-art results through scaling and mixed modality pre-training. Section: Algorithm and Hardware Simulation. In this section, we explore how well bGPT can simulate algorithms and hardware. Our main goal was to see how bGPT performs when dealing with different sizes of binary data. Since there weren't any standard models or datasets to compare with, we decided to test bGPT's abilities by increasing the amount of data it had to work with. We did this through two main tasks: converting data and modeling the state of a CPU, using data sizes that ranged from 1,000 to 1 million units. For the data conversion task, we used a dataset called Irishman, which contains music in both ABC notation and MIDI files. We tested this on data sizes from 1,000 to 100,000. For the CPU state modeling, we used a dataset that included different CPU states, testing on sizes from 10,000 to 1 million. When converting between ABC notation and MIDI, we were looking at how bGPT could handle both human-readable and binary data formats. Previous studies didn't directly model MIDI because of its binary nature, but bGPT is well suited for this since it can work directly with binary data. We measured the model's performance in both directions of conversion and found that as we used more data, the model got better at converting the data, showing lower losses and faster learning. Specifically, the bGPT model with 100,000 units of data performed exceptionally well in converting ABC to MIDI, almost reaching perfect performance. This was a significant improvement over the model with only 1,000 units of data. We noticed that converting from ABC to MIDI was generally easier for the model than the other way around. This is likely because converting from MIDI to ABC requires the model to infer more information that isn't directly present in the MIDI files. In the task of modeling CPU states, we aim to predict changes in the CPU's internal states based on machine instructions. We chose the most likely byte at each step, comparing the model's predictions to actual CPU states. Here, we also found that having more data improved the model's performance significantly. The model with 100,000 units of data showed a remarkable improvement in accuracy, achieving near-perfect results. This suggests that bGPT isn't just memorizing the data but is actually learning to understand CPU operations. We observed a significant leap in performance at a certain point, which indicates that bGPT might be developing a deeper understanding of CPU states. This supports the idea that large language models can develop new abilities as they are trained on more data and become more complex. However, Some might argue that these improvements could be due to the model just getting better at the specific tasks it was trained on, rather than truly understanding CPU operations. Overall, our findings show that bGPT is highly capable of simulating algorithms and hardware, especially as the amount of data increases. This suggests that bGPT and similar models could be very useful for simulating and reverse engineering a wide range of algorithms and hardware, even though the tasks we tested were relatively simple.